Hi everyone, so today we're going to be looking at Hess's Law, just to get some better understanding of what it is and just kind of get a better understanding of what it has been, just so we have a clarification. So Hess's Law, So Hess's Law is something that looks at the change in enthalpy in a chemical process. So chemists have determined that the change in enthalpy is a chemical process which is independent of the path taken. Which means, in summary, is that there's more than one way to go for a reactant to get from point A to point B. So in this situation here, to get from point A all the way to point B, we can take two different pathways. We can take a pathway that is 2 steps, which goes from H2 to the change in 3, or we can do a 3-step in order to get to B, which is our final destination, which is a change in enthalpy 4 to 5 to 6. And so the summary of this is that there's literally more than one way that we can get to our final product. And that's what Hess's Law is that if you want to get to the same destination, there's going to be more than one way. Another example is 2 students start at the same place and end up at the same place, but they can take different pathways to get there, okay? One person can go all the way over these mountains and all the way around just to get to this end, or one person might take another way and just get straight there. So that's what Hess's Law is. So in order to determine the overall change in enthalpy of an unknown reaction, we sum the known equations and the respective change in enthalpy values. So there's some rules when adding the equations. So these rules are, so if we have an identical element or molecule that is on the same side of the equation, then we're going to add their coefficients. If they're on opposite sides of the equation, then we're going to subtract their coefficients. And then from there, we're going to take the sum of the individual change in enthalpy to calculate the reaction. So that's the unknown chemical reaction change in enthalpy. So here are some rules that we're going to follow when using Hess's Law to calculate the enthalpy changes for our chemical reactions. The first is if you reverse a chemical reaction, you must reverse the sign of change in enthalpy. Okay? The second is if you multiply the moles of an equation by the specific factor, you must multiply them by the same factor. And then if you divide the moles of an equation by a specific factor, you must divide the same. Okay, so we're going to look at this example together just to get a better understanding of what is going on. So Hess's Law looks at endothermic and exothermic. So in this situation here, this formula is exothermic. So if we were to reverse the reaction, the result reaction would be endothermic. So therefore, if we were to reverse this, it would be H2O, which is our gas, and that would be reversed to H2O, and that is a liquid. So that means our change in enthalpy is going to be 88 kilograms, okay? Because we're reversing it. It's now positive. It's not negative anymore, okay? So that is what happens, is that we're reversing our reaction. So if we take the exact same equation and multiply it by a factor of 3, then the enthalpy change will also be multiplied by a factor of 3. So if we multiply this by a factor of 3, that means this final equation all has to be by a factor of 3. So if we now do times 3, so this 2 is going to be times 3, and we're going to get 9H2O, and that's going to be converted to 9H2O, which is now a liquid. This was a gas. Therefore, our change in enthalpy, we're going to have to also multiply this, okay? So therefore, if we multiply, we'll get negative 792. Okay? So that's because we are changing the enthalpy of the situation, and that is what we have to get. The reason why we got 792 992 is because this is a 9. So we have to multiply this also by 9. Okay? And that is how we get our change in enthalpy. So we're going to look at the following examples. We're going to calculate the change in enthalpy for the reaction and draw the enthalpy cycle. So we have our equation here. So based off of this information, we need to find that. So our goal is to use our reaction 1 and our reaction 2, which is given to us, to get the original reaction. So we must get the same moles and reactants and products as the original equation. Okay, so that's what we have to do. We need to get the same exact equation. So somehow we're going to need to manipulate reaction 1 and reaction 2 to get 4 PCl5, and we need to make sure that's all on the same reactant side, and then 1 mole of P4 and 6 moles of Cl2 on the product side. Okay, so our goal at the end of this is to literally get this entire equation written out from these two reactions. So let's calculate this information. So step 1 is to look at the first compound in the reaction that you were trying to calculate to find the enthalpy change. So reaction 1 looks at PCl3, and this is on our reaction side. But because we're going from 1 to 4, we need to multiply this by 4. Okay? And in order to do that, we need to multiply the entire reaction by 4. So therefore, we're going to multiply that by 4. We're going to get 4 PCl5. Okay? Oh, sorry, 3. Change it out. 3, because this is a 3, not a 5. Plus 4 Cl2, and that's going to convert to 4 PCl5. Okay, so therefore, the change in enthalpy, because we have to do the same thing, is going to be negative 2,996.8 kilojoules, sorry. Okay, so that is what's going to happen. We need to take our reaction, we need to convert it all over so we can have some way similar numbers here. So taking that information from reaction 1 to make it as closely similar to what our final product is going to be. Okay? So everything is multiplied by 4. Now, given this information, we are now left off with the following information. And we need to make sure that we are now following step 3. So step 2 said from the given data, try to find the reaction that has the same compound as in step 1, which we did. So now step 3, from the given data, try to find which reaction has 1 mole of P4 on the product side. So P4 on the product side, if we look at both of them, P4 is on the product side, so that is reaction 2. And that is P4 on the product side. So, based off this information, you now have used reaction 1 and reaction 2 at least once. Okay, so reaction 1 has changed because we have 4 PCl3 now, and we converted that all times 4. And now we have reaction 2. Okay, the reason why we needed to make sure that we had P4 on the product side was because that's where P4 was. Okay, so we know that that's where the information is, and so we can easily find our original statement based off of that. So continuing on, when adding the equations, if the same substance appears on opposite sides of the equation, we subtract their coefficient. So this is where now we're taking this valuable information and going back to those steps. So if the same substance appears on opposite sides of the equation, we subtract their coefficients. So our Cl, so our chlorine, is on opposite sides, so therefore we're going to have to subtract their coefficients. So we're going to do that afterwards. If the same substance appears on the same side of the equation, we're going to add their coefficients. So we know that PCl5 appeared on the same side, so therefore that's what we're going to use. And then we're going to add their enthalpy changes to get the enthalpy change of their original equation. So since scratch this one out. Since PCl5 is on opposite sides and they have the same coefficient, they cancel each other out. Okay? PCl3 stays the same, so it's left there because it's the same as the original statement. P4 stays the same because it is on the same side, and we need that information. And then we see that there are 4 Cl2 on the reactant side and 10 Cl2 on the product side. So when we subtract the 2, we get 6 Cl2 remaining. So therefore, since the products have more Cl2, the 6 Cl goes to the product side. So based off of this information, our PCl5 gets canceled out because they're on opposite sides. We are left with 4 PCl3. Okay, that remains on the reactant side. Now, what is left? We just discussed previously that for our P4, that stays the same, so we're going to leave the P4 there. Now we have our chlorine. So our chlorine is where it's going to be affected. So because they're on opposite sides of one another, we now need to subtract. So we're going to be left with 6 Cl2 because 4 minus 10 is going to leave you with 6. And so we get 6 Cl2, and that continues to stay on the product side. And that is our equation that is similar to the original one. The difference now, in order to find the difference of enthalpy, is we're going to take our two products and subtract them from one another. Okay, so if we do that, and we take our negative 2996, and we add those two together, we will get 7317.2 kilojoules, and that is left over. So remember, that is our goal at the end, is to find the change in enthalpy between the two in order to find our final product. And so that is how we manipulate it in order to find our answer. Let's do some more examples together because that can be very confusing. And so let's go more over it, okay? So now, for the next sample, we're going to calculate the change in enthalpy for the production of ethane using Hess's law. So here is the question. We have ethane gas, and it is going to be is used for the synthesis of plastic polyethylene. Engineers designing a process to make ethene from ethane gas, and they need to know the change in enthalpy of the desired reaction represented by the following balanced chemical equation. So first up, we see that reaction 1 has C2H6. Okay, so we see reaction 1 is similar. So we're going to leave it alone. The next part here, for number 2, we see that it is the reverse of reaction 2 and 3. Okay, so we can see that it is different. They're the reverse of one another, and the products are on the same side as the desired equation. So therefore, we're going to reverse the sign of our change in enthalpy. And this one also goes for later on our step 4 and 5. So we're going to create our new equation now. So we're going to reverse some stuff. So we are going to reverse our equation from 2 and our equation from 3. So we're going to recreate an equation, and we're going to name it 4. Okay? So we're going to reverse number 2 right now. So we're going to be left with 2 CO2 plus 2 H2O, and that is going to create C2H4 plus 3 O2. And then that's going to be a change in enthalpy of 1411 kilojoules. Because it was negative, we reversed it. Also for number 3, we're also going to reverse this one. Okay. For this one here, we're just going to change some things around. So we're going to reverse it because it is also negative as well. So we're going to reverse this one. So we're going to have 2H2O. That is going to create 2H2 plus O2 because we want to have this hydrogen on the other side. And so for this also, the change in enthalpy is going to be 572 kilojoules. So that negative symbol is going to be positive. So the reason why we reversed this is because we wanted to make sure that our hydrogen went to the other side, because that is what our equation is. So our first step is literally just to look at the different reactions here and see what reaction matches up, and if we need to reverse it, we will. So for reaction 1, this was fine, so we kept the reaction the same. For reaction 2, we had our O2, which we wanted to move over, but we also had C2H4, which reaction 3 doesn't have that, so we needed that to switch over. And then on top of that, we had our H2, which we needed that to also be on the other side in order to reverse it. So we reversed everything. So now that we have manipulated the reactions in a way that's going to work for us, okay, we are going to solve. So we are going to manipulate the following. CO2 is going to cancel out. Okay, they're going to cancel each other out because they're on opposite and same coefficients, so they don't appear in the final equation. Then we're going to look closely at water. If we look at reaction 2 and reaction 3, we can add water to get 3H2O, same side, and we're going to do this all in a moment. Okay, and then we can also cancel O2 because this does not appear in the final equation. So always check the coefficients of all the entities in your equation, okay, to make sure that if you see any, they must be adjusted by a factor so they can equal to the coefficient in the desired equation, okay? So therefore, we're going to have to multiply the change in enthalpy by the same factor, so make sure we're always doing that, okay? So if we go back to the numbers that we used, okay, we're just going to rewrite them out onto this slide just so we have some space. So we're just going to rewrite everything out that we are manipulating. So we have our first reaction, which is C2H6 plus 3.5O2. That creates 2CO2 plus 3H2O. The change in enthalpy is negative 1559 kilojoules. So that was the first one that we had. Then we had number 4, which was 2CO2 plus 2H2O. That creates C2H4 plus 3O2. Remember what our end goal is. Our end goal, I'm going to write it up here, is C2H6, C2H4 plus H2. Now, for 5, we had 2H2O, 2H2 plus O2. Change in H is 572 kilojoules. I forgot to write 4 out, which is 1411 kilojoules. All right, now, remember, for number 5 now, looking at all of our information here, number 5 has 2 moles of H2. We have nothing in here to help cancel that out. Okay, we don't have anything. And our product of H2 doesn't have any. So we're going to have to multiply by 0.5 to cancel that out. Okay, so we're going to have to multiply this entire equation by 0.5 in order to get rid of this 2. So therefore, we're going to have 6 now. So we're going to be left with H2O, H2 plus 0.5 O2. So that means we are now done with this one. And we're going to just solve with the following. But remember, our change in enthalpy now has to also change, which is going to be left with 286 kilojoules because we changed the entire equation. Okay, so now we're going to add all of these up now. Okay, so given all this information, we're going to add everything up now. So based off this information, we had our C2H6, okay? That was from the beginning here. Comparing everything else, okay? What we can do is start crossing things off. So we had 2 CO2 over here, and we had 2 CO2 over here. We can cross those off. Now looking at the rest of our work here, we had our 0.502, we had 302, which is 3.502, so therefore we can cross all of that off. Now we had one more thing, is that we had our value, so cross that over. We had our C2H4, we can add that, C2H4, that was on our information. And what is left over is we have H2O, okay? We have one H2O here, and then 2 here, that gets crossed off with our 3 on the other side. And so what is left over is our plus H2. So it's literally just trying to find everything to see where it is and what order we're gonna go in. Now, based off of this, we are going to do the following with our equation. So we have negative 1,559, we have 1411, and we had 286. If we take all of those values and add them all together, we will get a change in enthalpy of 138 kilojoules. So therefore, if we compare this originally to our beginning equation, we will find that that is the correct equation that we had at the very beginning, and therefore it works out. Okay? So, looking over everything, once we canceled everything out, we added everything together, and we got our answer to our equation. So our change in enthalpy is 138 kilojoules. Okay, so it's literally just organizing everything over and over again to making sure that it will fit, and then we can cancel things out. Okay, so always look at your equations, the reactions that are given to you. Can we manipulate them in a way that's going to match up to the original equation? Do we have to reverse them? What do we have to do? Once we've settled on our reactions, make sure we change our enthalpies if we change anything to our reactions. Then we start canceling things out. Does our reaction match our original? And if it does, fantastic. Make sure you add all your reactions to find the change in enthalpy. All right, if you have any questions, please let me know.